Now we study how to solve equations near a regular singular point using power series. Okay, so we study the equation we study is this equation. Second order the linear variable coefficient equation. The coefficient PQR has a singularity at x0, which means that Px0 is 0, and Qx0 and Rx0, at least one of them is not 0. Such x0 is called a singularity, a singular point. Okay, so solution of this kind of equation is not always analytic. Okay, it turns out that we have example of equation of this form whose solution is not analytic. Therefore, we could not expect to find a solution as the last lecture about the ordinary point. If x0 is an ordinary point, we can find a solution using power series. Okay, and we only need to determine the coefficients an, then which is a solution of our equation. But that only works for the case that x0 is an ordinary point. That is, px0 is not 0. But now our px0 is 0, so that method will not work because solutions of this singular equation might not be analytic. So if the solution is a power series, it means that the solution is analytic. So this is not possible, not always possible for our equation, which x0 as a singularity, singular point. Okay, so what should we do? For general case, we have no idea, but for some restriction, that is, we restrict to the case that the singularity of the quotient Q divided by P and R divided by P at x0 are not too bad. Okay, when the singularity of the quotients Q over P and R over P are not too bad at x equal to x0, we can find the solution of our ODE using series. Okay, let's see what to do. So firstly, we introduce a definition. The singular point x0, we said that it is a regular singular point. Regular singular point. Relatively, we also have irregular singular point. We will not study irregular singular point. We only study regular singular point. Okay. So if for x, what it means for x0 to be a regular singular point, if the following conditions are satisfied. Firstly, x minus x0 multiplied the quotient of Q over P is analytic. That is, it can be expanded as the Taylor series or a power series. Okay, in the neighborhood of x0. Okay, this is the first condition for x0 to be a regular singular point. The second condition is that the square of x minus x0 multiplied this quotient R over P is also analytic at x0. That is, it is also a power series. If these two conditions are satisfied, we say that x0 is a regular singular point. Okay, this is the definition. In this definition, we have not required that PQR are polynomials. PQR can be any functions as long as the corresponding x minus x0 Q over P and the x minus x0 square R over P are analytic at x0. Such x0 is a regular singular point. If x0 is not a regular singular point, we say that it is an irregular singular point. Okay, as I said before, we only consider regular singular point. So we don't require PQR to be polynomial. So if PQR are polynomials, when will x0 to be regular singular point? It's sufficient to assume that this limit is finite. These two limits are finite. If these two limits are finite, the LQ and LR are finite number, then you can prove that x0 is a regular singular point. That is, the analyticity of this function and this function can be guaranteed, can be true. Okay, so for polynomial, to verify that x0 is regular singular point, we only need to study whether these two limits exist and finite. But for general coefficient PQR, which are not polynomials, you have to investigate whether the corresponding functions can be expanded by a power series. Okay. So x0 is a regular singular point means that this function q over p, we denote by small p, is not too bad. It's not worse than x minus x0 power minus 1. Okay. This function is a singular function. This function is singular at x0. But our condition means that this function small p is not bad, not too bad, at least better than this function. Okay, and also another function capital R over capital P denoted by small q is not worse than this singular function. Okay, this is the meaning of regular singular point. So we don't go to more detail about this. What it means by not worse than, we don't want to explain this in more detail. Okay. Now we consider some example. So this is a equation, linear equation of second order. Variable coefficients. The coefficients are polynomials of x. Okay. So we are required to determine the singular points of this equation, and also classify them whether the singular point you found is regular or irregular. Okay, let's see how to do this. Firstly, we find singular point. Singular points are precisely where capital P, the coefficient of y double prime, is 0. So from this you can see that singular point, we have two singular points. One is x0 equals 0. The other is 2. These are the singular points of our equation. Now we need to determine 0 is 0 a regular singular point, and how about 2? How about x0 equal to 2? So we study x0 equal to 0 first. So because the coefficient here are polynomial, okay? Because the coefficient of our equations are polynomial, so to determine whether x0 is a singular point, we only need to consider these two limits, whether these two limits are finite number. If these two limits exist and are finite, then x0 is a regular singular point. But this is only work for polynomial coefficients. But now we are studying polynomial coefficients. So we consider when x goes to 0, this is whether this function has a limit. But this function is precisely this function. X minus 0 is x, q is 3x, p is 2x, x minus 2 squared. So simplified this equation, we obtain 3x over 2x minus 2 squared. Okay, and when x goes to 0, this goes to 0. Okay, so the limit is the limit for capital Q is finite. It is 0. Similarly, we consider the limit about r, that is x minus 0 squared r over p. So substituting the corresponding r and p inside this expression, we see that this is x squared x minus 2 over 2x x minus 2 squared. Okay, and simplified this is function. This is x over 2x minus 2. And the limit is 0. Sorry, I make a mistake. The limit should be 0. Okay. not a half. Am I wrong? I think I'm right. This is a misprint. This should be 0. Yes, this should be 0. So because the limit, both limits are finite, this implies that x0 equal to 0 is a regular singular point. Okay. Now we consider another singular point, that is x0 equal to 2. For x0 equal to 2, we consider when x goes to 2, this function. This function is precisely x minus 2, 3x over 2x x minus 2 squared. And this is 3 over 2x minus 2. When x goes to 0, x minus 2, when x goes to 2, x minus 2 goes to 0. Therefore, this fraction goes to infinity. So the limit is not finite. So this means that x0 equal to 2 is an irregular singular point. Okay. So even if this limit is finite, suppose in our case the limit is finite, you still need to verify whether x minus 2 squared rx over px has a finite limit. Okay. But when we obtain the infinite limit for the first limit, therefore we don't need to verify the second limit. But if the first limit is finite, you need to verify the second limit. That is the limit about r. So if the first limit is finite, you need to see whether this is finite. Okay. So this is the example about polynomial coefficient equation. Classification of singular points. Okay. Now our next example, this equation, we also need to verify, determine the singular point and classify whether they are regular or irregular. So the first step is to find the singular point. That is those x making y double prime, the coefficient of y double prime to be 0. But the coefficient is x minus a half of pi square. So this is 0 means that this equation has a unique singular point, that is x0 equal pi over 2. So our next question is to determine whether this singular point is regular or irregular. So how to study this? Now our coefficient, this is a polynomial, but the coefficient of y prime and y are cosine and sine. They are not polynomial. So to study whether this singular point is regular or not, we could not just study whether the two limits are finite. We need to how to say? So as x goes to x0, this function we need to study. This function equal cosine x over x minus half of pi. So when x goes to x0, that is half of pi, the denominator goes to 0. The numerator is also cosine x also goes to 0. Therefore, this is 0 over 0. But we can apply the hospital law to compute this limit. This limit is equal to the limit of minus sine x over 1. The limit is minus 1. Here I use this symbol the meaning of this symbol is that both sides, the left hand side and the right hand side, has the same limit. Okay, so I just for simplicity I introduce this symbol to mean that in the limit we study the left hand side, the limit of the left hand side equal that of the right hand side. So this limit is finite, minus 1, and the limit of the other function is also easy to compute, that it is also a finite number. So although both limits are finite, but we cannot declare that this x0 is regular. Okay, why this is not regular? Because the limit test mentioned here only works for polynomial. Only for polynomial we can determine that the singular point is regular. if these two limits are finite. But in our case, although the two limits are finite, but because the our coefficients are not all polynomials, so the limit finite does not imply that x0 is a regular singular point. So therefore we have to study the analyticity of these two functions near at the point x0. Okay, so we have to check analyticity at the singularity. So to expand this function x minus x0 q over p, by our computation, this is precisely cosine x over x minus pi over 2. So we need to expand this as a power series of x minus pi over 2 because the singularity is pi over 2. So we need to compute. We want to expand cosine x at x equal to pi over 2. Therefore, we compute the derivative of cosine x. Cosine x, the case order derivative of cosine x is cosine x plus k pi over 2. This is cosine, this is misplane. So the value of the case order derivative at the singularity pi over 2 is cosine k plus 1 pi over 2. Therefore, the expansion of cosine at pi over 2 at the singularity is given by this series. And this series can be simplified because cosine, the derivative is cosine k plus 1 pi over 2, and this can be computed. So when k is even, this is 0. When k is not even, this is minus 1, a power of minus 1. Therefore, this sum only has the old term. We only have old term of this. Okay, old k denoted by 2l plus 1. 2l plus 1, so the k is 2l plus 1. So the power k is also 2l plus 1. And the cosine 2l plus 1, that is 2l plus 2 pi over 2. That is k plus 1 pi is the power l minus 1 of minus 1. Okay, so this simplification is easy. Calculus, we know. Okay, so the expansion of cosine x, which respect to at the point pi over 2, is given by this series. Therefore, this function is cosine over this, and then we use the expansion of cosine. So the cosine has a factor x minus pi over 2. This can be cancelled. One of them can be cancelled with the denominator. Therefore, this gives us the same expansion as cosine, but the power of x minus pi over 2 is 2l. Previously, for cosine, this is 2l plus 1, but we cancel pi minus half of pi 2, which is the denominator here. So we only have 2l here. And as you can check, the radius of convergence of this series is positive. Actually, I believe the radius of convergence is for all is infinity. So this series converge for all x. So this means that this function is analytic. Okay. Similarly, the other function we need to investigate is sine x. So this is also analytic. Therefore, our conclusion is that x0 is a regular singular point. Okay.